This work is not new physics, but rather old physics that is recovered or restored from the late 19th century, early 20th century, when it was believed by Hendrik Lorentz and Henry Poincaré that an ether privileged reference frame exists that ensures invariance of the Maxwell electromagnetic equations and physics in general. The Hubble expansion and CMB plus dipole discoveries have made it possible to bring the Lorentz-Poincare privileged reference frame theory into the 21st century. It is with this recovery and restoration of the original relativity physics that the time shift attending the isotropic light speed assumption becomes evident. In this introduction chart, we first note that the later chart 13 may be considered the focal point of the presentation, in that Einstein and also Lorentz-Poincaré in their own reasoning effectively shifted or rotated the cumulative time slowdown trace to give synchrony along the x-prime axis and, as a consequence, to give equivalence between all inertial reference frames. As a presentation overview and to provide background for chart 13 and the presentation in general, 5 charts from a Lorentz transformation derivation presented at the 2024 APS meeting are included. Regarding the present work, the principal developmental charts are numbers 10 through 14, wherein the relativistic CM frame theory is compared in relation to Einstein's isotropic light speed theory within the same CM frame. Comments are provided in the concluding notes. This chart suggests that the reciprocal and non-reciprocal approaches at the foundation of relativity physics be joined in a complementary relationship to best address modern challenges. As a partial reiteration, Hendrik Lorentz and Henry Poincaré, two pioneers of non-reciprocal ether/PRF privileged reference frame relativity theory and of early relativity physics, concluded with Einstein that it is best to adopt a simplifying isotropic light speed at the foundation of relativity physics due to the failure of the Michelson-Morley experiment to detect motion through the ether. Failure to detect meant adoption of the simpler isotropic light speed assumption instead of the non-measurable anisotropic light speed. But now, discovery of the cosmic microwave frame with its average 369.8 kilometers per second dipole at the Earth's location, along with a time shift within the CM frame, means that the Lorentz-Poincare privileged reference frame theory may be returning. Because of the CMB discovery and the time shift within the CM frame, the Lorentz-Poincare theory may be brought into the 21st century, where it should join with special relativity in a complementary relationship going forward. This chart gives the history of the inertial reference frame development leading up to the suggested accommodation between Lorentz-Poincaré's non-reciprocal cosmic reference frame and Einstein's reciprocal special relativity in order to best address the later 20th century observational discoveries and challenges. This chart and the next 4 charts comprise part of the 2024 virtual presentation entitled Derivation of the Lorentz Transformation Accounting for Two-Way Speeds of Light in the Moving Inertial Reference Frame, which 5 charts are provided as background information in the present set of charts. In the present chart, we derive the time and length contraction equations assuming time-averaged anisotropic light speed c plus or minus from the moving IRF origin along the x-prime axis to a remote location and back to the origin. This is the second of the 5 background charts carried forward from the 2024 American Physical Society meeting in Sacramento, California. In this chart, we derive the spatial part of the Lorentz-Poincare transformation and do so on the non-reciprocal basis
that is consistent with the discovered CMB plus dipole, giving the universal CM frame. This non-reciprocal basis differs from Einstein's reciprocal basis by providing a more direct and also more general understanding of the relativity physics of the moving IRF in relation to the relativity physics of the stationary IRF.
In this derivation of the spatial part of the Lorentz transformation from the 2024 annual meeting in Sacramento, California, the moving inertial reference frame is shown in red and the stationary frame is shown in black. Here the stationary IRF basis vector is shown to retain its original at-rest length when same motion accelerated into the moving IRF, with the three accelerated clocks each being physically contracted along the direction of motion, but not shown as contracted in the chart. Applying the basis vector length contraction equation gives the spatial part of the Lorentz transformation.
This is the fourth of the 5 background charts carried forward from the 2024 American Physical Society meeting in Sacramento, California. In this chart, we introduce the derivation of the temporal part of the Lorentz-Poincare transformation and do so on the non-reciprocal basis that is consistent with the discovered CMB plus dipole, giving the universal CM frame. This non-reciprocal basis differs from Einstein's reciprocal basis by providing a more direct and also more general understanding of the relativity physics of the moving IRF in relation to the relativity physics of the stationary IRF. This is the fifth and last of the 5 background charts carried forward from the 2024 American Physical Society meeting in Sacramento, California. In this chart, we derive the temporal part of the Lorentz-Poincare transformation and do so on the non-reciprocal basis that is consistent with the discovered CMB plus dipole, giving the universal CM frame. This non-reciprocal basis differs from Einstein's reciprocal basis by providing a more direct and also more general understanding of the relativity physics of the moving IRF in relation to the relativity physics of the stationary IRF.
This chart is an introduction to the next 4 charts, which compare Lorentz-Poincare non-reciprocal privileged reference frame relativity to Einstein's reciprocal special relativity, leading to the recommended complementary relationship. This chart encapsulates the Lorentz-Poincare complementary theory by way of a clock slow moved through the CM frame along the x' axis. Because it moves slightly faster than the moving IRF, it gradually loses time relative to its moving IRF and reaches minus 7.018 seconds at 7.09 light seconds from the origin. In this brief discussion of Lorentz-Poincaré's CM frame complementary theory, we are now well into the 21st century following the Hubble expansion and CMB radiation discoveries. The latter with its 369.8 kilometer per second dipole at the Earth's location. And these considerations suggest a complementary relationship between co-moving CM frame theory and special relativity to attack ongoing problems on a broader front. The difference between this chart and that of Lorentz-Poincaré's CM frame complementary theory in chart 11 is the isotropic light speed assumption, which directly eliminates or reverses the minus 7.018 second time shift that occurs in the CM frame theory. Here we recognize that all 3 principal relativists at the time, Einstein, Lorentz, and Poincaré, assumed isotropic light speed because of the null Michelson-Morley experiments. Now, however, the Hubble expansion and CMB plus dipole discoveries give credence to the CM frame existence thereby also crediting the time shift within the CM frame relativity.
Adding to the comments of the previous slide, the last paragraph of the present chart reads, notwithstanding Einstein's making the irreducible basic elements as simple and as few as possible, or perhaps because of it, special relativity has proved useful on a broad front and should continue in the parallel complementary capacity in relation to the Lorentz-Poincare CM frame relativity physics.
The prime takeaway from this presentation is the recommendation that the Lorentz-Poincare privileged reference frame relativity, now continued within the CM frame, and Einstein's special relativity be considered complementary space-time theories as we address ongoing physics and cosmology problems. This is an admittedly remarkable turnaround or development after the very early 20th century, when Lorentz, Poincare, and Einstein separately assumed isotropic light speed as a necessary simplification in light of the failure of the Michelson-Morley experiment to detect an ether-based privileged reference frame. But the later discoveries in the 20th century of CMB radiation with its 369.8 kilometer per second Doppler dipole at the Earth's location, along with Hubble expansion, revealed the crucial CM reference frame.